Sorry I couldn't make it today, guys. My son is sick today, so your test will be tomorrow. I'm sure you're very upset about that, but it is what it is. So let's just go over some of those review questions. I'm not going to go over every single one here, but let's just go over like the last page, so like 16 through 24. So 16 is pretty straightforward. They just want this acceleration. So this is just a Newton's second law equation. So we know F net is equal to ma, and they want acceleration, so a is just F net over m. So they give us the net force of 150 newtons. Remember, 150 kilogram meters per second squared. Though you know those are units for newtons too. And then we'll just divide that by the half kilogram. This just gives us an acceleration of 300 meters per second per second. So that was pretty straightforward. So let's get to the number 17, because number 17 is what gives people problems, because this is the elevator problem. So what we have to remember is the normal force. The normal force is what the bathroom scale is going to read. So when this one says person with a weight of 490 newtons, we should also note that this 490 newtons, this is the person's weight. This thing right here is the weight. It is not the mass. So let's keep that in mind. So what does the scale read? Remember, this is our normal force. So for all these, again, like we can just draw a free body diagram. If the person is moving at a constant speed or stopped, their normal force and their weight will be the same. So I can write my second law equation. I know F net equals ma. So what is F net? F net is the combination of both of those forces. Because they're equal, it doesn't matter which one I put first. So I'm going to put Fn first because I feel like it. And I know it's not accelerating, so I can set this equal to 0. So I know that Fn is equal to mg. They told me mg. Mg is the weight. This is 490 newtons. So therefore, Fn is equal to 490 newtons. All right, let's move over to question B. So question B says, question A. So when the elevator starts to ascend and accelerates the person up at a rate of 2 meters per second per second. So here's my free body diagram. I made Fn bigger because if it's accelerating up, the net force is up. So once again, I'm going to write my second law equation. F net is equal to ma. Just like before, what are my forces? My net force. My net force is the combination of those forces. Well, now I got to be careful which one I put first. It's always the bigger minus the smaller. So now I need to put Fn minus mg. Now I have to do that this time. But now it equals ma, because my acceleration is no longer 0. If I want what the bathroom scale reads, I have to keep the Fn. Fn equals mg plus ma. So mg is 490. So now I have to figure the mass out, right? So we know that the weight, if I call it Fg or Fw, it's still equal to mg. Okay, so if I want mass, it's equal to my force of gravity over the acceleration due to gravity. Force is 490. Gravity is 10. Mass is 49 kilograms. This is 49 kilograms times 2 meters per second per second. This gives me a normal force of 588 newtons. All right, let's move on to B. So now B says the elevator reaches its speed, it no longer accelerates. So what's the reading on the scale as it arrives at this speed? So because it's not accelerating, therefore the net force is 0, therefore the scale is going to read his exact weight, which is 490 newtons. So then C says If the elevator begins to slow as it reaches its proper floor, do the scale readings increase or decrease? So let's real quick do a free body diagram of this. So I know I have mg down, and then I know I have the normal up, right, or perpendicular to the surface. So now the question is it bigger, smaller, or the same as the weight? So if you are slowing down, you're moving up and slowing down, that means your acceleration is down. That means this force here is bigger than this one. So if your weight is 490, this has to be smaller than 490. Your acceleration is down, your net force is down. So the choice there is decrease. So now the elevator starts to descend. So it's the same thing, right? So if it's descending, that means the net force is down. If the net force is down, that mg is bigger than the Fn. That means the scale reading goes down. So if the scale reading, if it's moving at a constant rate, it reads the same as your weight. And then lastly, if the cable snaps, there's no scale reading at all. The floor can't push on you, so therefore there's no scale reading. All right, let's move on to number 18. So 18 says I want the acceleration at a force of 25 newtons gives a 4 kilogram mass, and the frictional force is 5 newtons. So let's do a quick free body diagram of this guy. So I'm going to assume this thing goes right, so I'm going to call the force applied here, let's call this the applied force. Then there's that frictional force they told me about, and then of course I got weight, and then I've got the normal force perpendicular to the surface. So just like always, I'm going to do my F net is equal to ma. So my net force is really my Fa minus Ff is equal to ma. So if I want my acceleration, it's just F net over m. Fa minus Ff over m. So I have my applied force of 25. I've got my frictional force of 5 and 4 kilograms. So this gives me 20 over 4, which is going to be 5 meters per second per second. There's your acceleration. All right, so now number 19 wants us to find the mass of that metal blob. So remember, mass is just, to find the weight, we know weight is mass times gravity, so mass is just your weight or force of gravity over the acceleration due to gravity. So at number 19, the metal blob has a the force of gravity of 200, and they tell us that what's on Earth, so it's 10 meters per second per second, so it's just 20 kilograms. And I'm going to put some units on that guy too, so it's 20 kilograms. So 20, now it says how much does the blob in 19 weigh on Jupiter? So we're just going to go back and do the same thing again, but we're going to go to Jupiter now, where my force of gravity is just mass times gravity, and my mass is 20, and they say the acceleration due to gravity on Jupiter is 25. And this just gives me a weight of 500 newtons. So it weighs a lot more on Jupiter, as we would expect. All right, so now I got that same blob in 19, and we'll take it to deep space. So what does it weigh in outer space? Because gravity is 0, the weight is 0, so Fg is 0. Will it still have mass? Absolutely, it will still have mass. That doesn't change, it's still 20 kilograms. So will it still take a force to accelerate it? Absolutely, because if you want to accelerate it, it's just F over m, right? You want to accelerate it, you got to have a force. You can apply force to a mass, and it still has mass. So how much force will it take to accelerate it at 3 meters per second per second? Just 20 times 3, which is 60 newtons. That's how much force it takes to accelerate that guy. All right, let's get to the last page. So I have an applied force, I've got a frictional force, and I've got, of course, my weight and my normal force. So they want to know what the coefficient of friction is. So coefficient of friction is, remember, it's just how slippery something is, basically. So we can say this force of friction is mu times Fn. So if I want mu, it's just force of friction over Fn. So the easy one to figure out is the normal force, right? So if I know that this is not accelerating in the y direction, I know that the force, this weight, which happens to be 600 newtons, is the same as this normal force up here. So we know this is 600 newtons here. So now the question is, what's the frictional force? So this one's a little trickier. So now we're going to have to do equation in the x direction for this guy. Just like always, I start out F net is equal to ma. Because I'm in the x direction, I've got my applied force, I've got my frictional force, and I set that equal to ma. So it looks like I'm going to have to find my mass. So remember, we know our F sub g is equal to ma, right? Or mg. And I know that the weight of the gorilla is 600 newtons. I know the acceleration due to gravity on Earth is 10, so his mass is going to be 60. So I want to find this frictional force, remember. So this frictional force is just the applied force minus mass times acceleration. So the applied force, they tell me, is a big old 1,500 newtons, which is a lot, minus the mass, which is, we just figured out, is 60. And he's being accelerated at 4 meters per second per second. So this means the frictional force is this 1,260 newtons. So now I can bring that guy back over here. This should be 1,200, oops, change colors. We got 1,260 newtons. So this gives me a coefficient of friction of 2.1. It doesn't have a big coefficient of friction, but imagine, you know, gorillas can grip the ground pretty well. So, all right, so there is our 22. On to 23. So now I got a car on an icy road, crashed into a stone wall at 7 meters per second. And it comes to rest in 3 seconds. So this gives me a clue. I got this speed here and a time. You know what that means, don't you? That's right, the big 5. So if I want this force, I know F net is equal to ma. So because I have initial speed, the initial, I know it's going to, when it hits the wall, I know V final is going to be 0. It means I've got a time here, which means my acceleration is just really my delta V over t. So I can just put that right into here. I can just say it's m delta V over t. So I know the mass is 2,200. I know that my speed, my change in speed is going to be 7 meters per second, and I know my time is 0.3 seconds. So this gives me a whopping 51,333 newtons, which is quite a bit. I do recommend hitting walls with cars. All right. Now, lastly, so if the wall hits the car hits the wall with 51,333 newtons, that means the same force hits the car, because Newton's third law, right? Forces are equal and opposite. So your test is for sure tomorrow. Complete the work that the sub asked you to do, and good luck on your test tomorrow.